I want to get into a revisiting of probability distribution. Let me back up a little bit here. And we're going to see, I brought these girls up in 105 today. Because last class, we flipped coins and we rolled dice. Actually, we didn't flip coins. We rolled dice, we played Chuck-a-Luck, we analyzed my mortality through life insurance policies, all these wonderful things. But I want to make sure that you guys get a more micro look at this idea of a probability distribution. And here's an application of that I just adored. So here are the first 4 chickens my family ever owned. These were taken about 3 years ago. 4 years ago now, maybe? 4 years ago. Bertha, Mary, Marge, Nancy. Okay, so what you do is you go to High Desert Ranch and home, or wherever you get chickens from, and they've got these huge bins that look like this, full of birds. And there's a little heat lamp on them, and there's a food tray and a water tray somewhere. There's no water in this one. And you take your, well then 3-year-old, you go, Max, we want chickens, go pick some. And he's like, ooh! And he runs in and he grabs them. Now the sign next to the bin, says, these are, I don't forget what these are, these might be Leghorn pullets. And then they're like $1.50 a piece or something like that. A pullet, say that again.
It says do not touch.
It doesn't do not touch. It's hard to explain to a 3-year-old why you can't touch the chicken. But then once we get them in the box and bring them home, they put them in a little Happy Meal box to bring home. Then he can touch them all he wants. So anyway, a pullet is a female sexed chick. A female sexed chick. So when Max reached in and picked the girls he wanted, and here's him bringing them home that day. They come in a little box. There's a little box. There they are. Day old. They're called day olds because they're actually literally a day old. This is the more recent batch. We got 4 more since then. Back up to this then. So here they are again. There's Bertha, Mary, Marge, and Nancy. Okay?
Your child is adorable.
Well, he's pretty cute. Yeah, he's a keeper. So we'll come back to those. So I walked up when I paid for them, and I asked the guy at the store. I said, "Hey, so you say these are females?" He's like, "Yeah." And I'm like, "How do you know they're females? I mean, they're tiny. They're this." Well, they don't with 100% certainty, Sandy. See, that's what I learned. I learned that you don't know with 100% certainty. So I said, "Is it a coin flip?" Because literally, if you were to raise chickens from a rooster and a chicken, somebody in my neighborhood has a rooster. I can hear him in the mornings now. It's adorable. 5:30. I'm like, okay, I'm up. It's cool. But if you have that rooster fertilize eggs, then you're going to have a coin flip as to whether you get boys or girls. But these are sexed pullets, which means they've been identified. And I asked him, "How do you do that?" He's like, "Oh, we've got a very specific technique." I'm like, "Is it like lifting their skirt and looking?" And apparently it's not far off. It's checking something there. And he said they have 90% accuracy on identifying the sex of the pullets. And he was very proud of that. He's like, "Yes." And I looked down when he said that at this, and I said, "That means there's a 1 in 3 chance I got a rooster in this box." And he looked at me like I had 3 heads. He's like, "How the hell? First of all, that can't be right." That was his first. That can't be right. I'm like, "Actually, if your 90% is right, then my 1/3 is right." And then his next question was, of course, "How do you know that?" And then I sat down and realized, as I was talking to him, this would make a great 243 lesson on a very specific kind of distribution. So that's what I want to do with you guys today is, I want to analyze our chicken flock and show you how it ties into psychological and sociological and HDFS and natural resource distributions, all tied back to my chickens. And it's funny because today in 105 we were talking about this. I asked them the same question I asked you 2 or 3 weeks ago. When you flip a coin, what's the chance of getting heads?
Half.
It's half. What does that mean?
It means that it has an equal chance of being heads as much as it has.
Yeah.
That's a good answer. That's a good answer. It has an equal chance of being heads as it has of being tails. 2 outcomes equally likely. I heard somebody say over time, if I flip a coin lots and lots and lots and lots of times, what's going to happen?
50 out of 100.
Roughly half of the results will be heads and half will be tails. What don't you know?
The weight of the heads and the weight of the...
In any particular run, which ones are coming, right? You don't know which flip is coming next, but you know, looking at a past run, if a coin looks fair or not by looking at how it performed. It's that whole past performance does not guarantee future results. Well, on a coin, it should actually, unless the coin gets broken in some way. And then I asked the next question. I'm like, what's the chance I get a flat tire riding back from work today on my bike? And then one of the kids goes, well, either do or you don't. That's a great answer. Either do or I don't, so it's 50-50. And she's like, that's not what I meant. I said, what did you mean? If it's not 50-50, then what did you mean? And that was a much harder question, wasn't it? What is the chance I'm going to get a flat riding home from work today?
Depends on the probability, or depends on what happens on that road.
That's a good answer. That's a good answer. If I smooth it out and make the whole thing an average, we calculated it's about a 0.5 or 1/2 of 1% chance I'm going to get a flat today. If you look strictly at what has happened to me over the past 10 years, if you look at the run that I've had over the past 10 years, I've gotten about 1 flat per year-ish, riding to work, riding to and from work. Making that a 200-day work year, which is essentially what I do, I get 1 flat per every 200 days, on average. That of course loops in the time I got 3 flats in 1 day. I'll never forget that day. That was the day I almost stopped my commuting. I'm like, seriously? And then I'm like, outlier, dude, outlier. It's hard to be rational. It's hard to be rational and logical when you're pulling your 3rd flat of the day, which was a 4-inch long nail that went through your tire and ruined the entire rig. It's hard to be objective when you're swearing like a sailor, changing your 3rd flat of the day. But at the same time, you have to realize it's going to happen. It's going to happen at some point. You're going to get 3 flats in a day because somebody left a 4-inch nail on the road. Please cover your loads. Go to the dump. Thank you, friends. Say it one time. All right. So the question is, was I able to tell the guy that there's a 1 in 3 chance I got a rooster in here? How was I able to tell the guy that? Anybody figure it out right now? Please, Scott.
You took the probability of 90.90% and times it by how many chickens you got.
Ah, but that's chickens.
So, sorry. I
don't know what you're saying.
It's 0.9 times 0.9 times 0.9 times 0.9.
Thank you, sir. Are you seeing how this is tied back to your project from last week? If you're not, that's okay. That's okay. That's okay. I want to get back into that from last week. In case you forgot your project from last week, maybe you're trying to forget it, that's okay too. But I want to get back into that, and I want to show you how this is just an extension of what you did in that project. It's a more specific extension of that project, but it's definitely an extension of that project. Let's get back into a few things. First of all, the chance a chick is actually female is 90%, as per what the guy told me that day in the store. So we know that. Okay, now I want to go back to what Scotty just said. He said something very, very good. He said, if I had Max pick 4 chickens, the chance of getting a girl and a girl and a girl and a girl, or successive girls, is just 0.9 times 0.9 times 0.9 times 0.9. I want to go back to see if you can remember why he was multiplying and not adding those. Because this is an important thing to remember, when you multiply and when you add, probability-wise. So the probability that I get 1 girl is 0.9, 90%. Hopefully that's believable. So what's the chance I get 2 girls? Well, using the idea of your project, that means I have to get the first one to be a girl, and then the second one.
Keyword and.
Say that again, Randall.
Keyword and.
And the key word is and. The first word from your first project was or. When you or, that's when you add things. But the key word from the second project was and. When it's and, you multiply things. So what's the chance that the first one was a girl and the second one is also a girl? Well, this is when we started breaking it down in that project, and we started saying things like, what's the chance that first one was a girl? 0.9, 90%? What's the chance that next one is a girl? Now let's talk about that real quick. Let's talk about that real quick, okay? Just real quick, real quick. Can we say that it is exactly 0.9? Remember what Max had to do? He had to reach into this bin, and let's just assume for the sake of argument, he's pulling them all out of the same bin, for the sake of argument. So let's say there's 100 birds in that bin. 100 birds in that bin, right? And he goes in, grabs one, or asks the person at the store to take it out for him, so we obey their rules. 90% chance of that first one being a girl, right? What's the chance the next one's a girl? It's not really 0.9, is it?
No.
We just took a girl out, and we also took a bird out. So if the first one was 0.9, the second one really is 89 out of 99, isn't it?
89, yeah.
Isn't it? And Sandy's going, yeah, but, and I love that, because...
Is it relative? I mean, the probability doesn't necessarily change, it just, your sample size is shrinking.
Right, so it is changing,
relative.
but it's not changing enough to worry about. That's the thing. That's why Sandy's look is it worth worrying about? No. If there were only 10 birds in the bucket, I'd say it was worth worrying about, because then that means 9 out of 10 of them are girls. I grab one out. Now it's 8 out of 9, right? If I grabbed a girl. And then it's 7 out of 8. And then it's 6 out of 7. You see what's happening? The more I pull them out, that's changing significantly. We're dropping like 5, 6, 7 percentage points each time. But what's the difference between 90 out of 100 and 89 out of 99? Calculate it for me really quickly if you would. 89 out of 99 versus 90 out of 100. What's the difference? What's the difference?
89%.
Say that again?
It's 89.
89 and how much? 89.9. You see? Which is essentially 90%, isn't it? Now you got to realize there were way more than 100 birds in that bin and in the store at that moment. There were hundreds, if not maybe 1,000 or so birds in that bin. So in other words, the reason I'm stopping and doing this, the reason I'm stopping and bringing this up is it okay to put 0.9 here?
Yes.
I think it's okay, because even though it's kind of like 0.9 in quotes, mathematically we can assume it's 90%, because I didn't tell Max to go in and buy every bird in the store. If I told Max to go and buy every bird in the store, there's about a 100% chance I'm going to have a rooster in there somewhere, most likely.
And probably broke.
And be broke. And full of chicken poop after about 3 or 4 days. Yes, I put those birds in my backyard. So, everybody okay with that? It's fair to put the 0.9 in there. Okay, so then, let me turn the projector off for a second. So to get 3 girls, that means I gotta get the first one, let's just do it this way. The first one's gotta be a girl. And the second one. And the third one. So it'll be 0.9 cubed. Are you remembering your last project now? Good. Good. So it is definitely tied back to that. And it's the nice part of your last project. The part of your project you hated last time was the whole down by 1 thing. Down by 1, down by 1, down by 1. I know you hated that. I know you hated that. You totally hated that. You loved it. I loved it too, actually. But that's why I couldn't understand. Some people hate it. But it's understandable, because you have to keep track of all those down ones, down ones, down ones, down ones. I totally get that.
I see.
But even when you should do this down 1, because this, technically speaking, you should do this by a down 1 situation, you can get away with treating this with replacement. In other words, it's the same as Max going, checking a bird for femality, then putting it back in the bin, shuffling it up again, and then grabbing another bird. Gallup does this all the time when they do telephone interviews. When they survey 1,000 Americans, they assume that they are randomly selecting them with replacement to run their mathematics. They most likely aren't. Once they call a person, they're not going to call that person again. But they run the math as if they did, because think about why it would be annoying if they didn't. What's the chance that you get selected, for Gallup in a random digit dialing phone call?
1 out of 300.
1 out of 330 million, right? Now they've already picked somebody. What's the chance you get selected next? 1 out of 329,999,999. Who the hell wants to use that number? Let's just use 1 out of 330 million again. Why not? Because it's not that much different. That's why I put it in quotes. Oh, the only one that's truly 0.9 is the very first one. And then they start decreasing. But if you draw a small enough sample from a large enough population, it doesn't matter. That was the point of that one section of the project, the pumpkin seed deal. And the whole idea, you treat them as an independent coin flip each time. Fair enough? Please.
And so that's
Thanks.
how we can tell whether it's all right to use replacement or not, is if it's a big sample.
Yeah. When you have a large chunk that you're pulling a small batch from. Now, of course, what does that beg to define? What is that? Large and small, doesn't it? So here's a guideline to work off of for you guys as you go out into your lives to do this. If you're pulling less than 5% of the population, it's usually pretty safe. And you almost always are. You're hardly ever getting close to 5%, unless you're running a census. But if you're running a census, you got all the numbers anyway. There's no statistics left, it's parameters at that point. So if you're getting less than 5%, you're usually pretty safe as far as that goes. We only want 4 birds out of, 1,000 or so. That's way less than 5%.
So like the chi-square is essentially like when you're looking for like your data and you're proving hypothesis.
You have to make sure you draw a large enough sample to see the behavior.
Right.
And that depends on the assumed probability. You're taking 244, right?
No.
Well, then we'll talk about it then. Okay, good. It's not a simple answer.
No, that's-
It's not a simple answer.